Mass feels solid. It presses into your hands, anchors your body to the ground, and resists every attempt to move it. And yet, modern physics tells us something unsettling. At the deepest level, mass is not a substance at all. It is energy, arranged, constrained, and prevented from moving freely. That single fact has forced physics to rethink what matter really is. After Einstein wrote E equals mc squared, it became clear that mass and energy can transform into one another. But that equation never explained why some energy becomes matter in the first place, while the rest rushes across the universe at the speed of light. Why does energy sometimes settle into stable forms that can rest, push back, and endure? Tonight, we follow that trail carefully through quantum fields, the Higgs background, and the hidden energy locked inside protons, to see how mass quietly emerges from structure rather than substance. And that is where the story truly begins, with Part 1, where we take a closer look at why mass exists at all, even though energy itself is free to move. Energy, when left unconstrained, does not settle. Every verified observation in modern physics agrees on this point. Electromagnetic radiation propagates at a fixed speed in vacuum. Relativistic particles without rest mass never slow, never pause, and never define a frame in which they are stationary. From the earliest measurements of light to contemporary observations made by space-based instruments operated by NASA and ESA, energy appears to favor motion whenever nothing restricts it. And yet nearly everything we interact with behaves in the opposite way. Objects remain at rest. They resist acceleration. They persist as localized, durable structures. This contrast is not a surface-level curiosity. It marks one of the most persistent tensions in fundamental physics. When Einstein introduced the relation E equals mc squared, the equation was quickly verified through nuclear processes, stellar fusion, and particle annihilation. Each confirmation reinforced the same message. Mass and energy can be converted into one another with precise accounting. But the equation itself is silent on origin. It does not explain why energy sometimes exists in forms that allow rest, persistence, and resistance to motion. Einstein acknowledged this limitation directly. In correspondence and later writings, he treated the equivalence as a statement of balance, not of construction. The mechanism that allows energy to appear as mass remained unresolved. The path forward emerged only when physicists stopped treating mass as a material ingredient and began treating it as a relational outcome. Quantum field theory replaced the idea of particles as fundamental objects with a different framework. Fields are primary, particles are secondary. Every particle corresponds to a localized excitation of a field that exists throughout spacetime. Within this description, mass is no longer an intrinsic property carried by a particle. It becomes a feature of how a field responds to motion and interaction. This shift resolved an immediate inconsistency. If mass were an inherent substance, it would be difficult to explain why some particles are permanently massless, while others are not. But if mass depends on interaction, the distinction becomes natural. Fields that interact with certain background structures acquire modified energy-momentum relations. Fields that do not remain unrestricted. The Higgs field represents one such background structure. According to the Standard Model, the Higgs field occupies all of spacetime in a uniform state. It is not emitted by matter, nor does it dilute with distance. When certain fermion and boson fields interact with this background, their excitations acquire rest mass. This interaction alters the relationship between energy and momentum in a way that allows a rest frame to exist. Experimental confirmation arrived in 2012 with the detection of the Higgs boson at CERN. The measured properties of this excitation matched predictions with remarkable accuracy. Subsequent measurements refined the coupling strengths between the Higgs field and known particles. Photons, notably, showed no coupling at all. As a result, they remain massless under all tested conditions. Electrons and quarks, by contrast, couple to the Higgs field and therefore can exist at rest. Yet this success immediately exposed another limitation. The Higgs mechanism accounts for only a small portion of the mass of ordinary matter. Detailed calculations show that the Higgs-generated masses of the up and down quarks inside a proton contribute only a few % of the proton's total mass. The remaining mass must arise from a different source. That source is found in quantum chromodynamics, the theory describing the strong interaction. Protons and neutrons are not simple assemblies of massive components. They are bound states maintained by gluon fields that confine quarks within a limited region of space. These gluon fields are massless, yet they carry energy and momentum. Because of confinement, that energy cannot propagate freely outward. It remains stored within the bound system. This conclusion is supported by decades of experimental work. Deep inelastic scattering experiments, beginning at SLAC in the 1960s and continuing through modern collider programs, revealed that gluons carry most of the momentum inside protons. Lattice QCD simulations, developed over many years and refined with increasing computational power, reproduce the observed proton mass using field energy alone, without assigning large intrinsic masses to quarks. In this context, mass emerges as a measure of how much energy is locked into a configuration that cannot be transformed away by changing reference frames. The confined gluon fields inside a proton define such a configuration. No inertial frame exists in which that energy disappears. As a result, it contributes to invariant mass. This understanding aligns with relativistic principles tested far beyond the laboratory. In neutron stars, observed by ESA's XMM Newton and NASA's NICA mission, matter is compressed to densities where individual nuclei dissolve into collective field states. The resulting increase in mass energy arises not from new particles, but from pressure, confinement, and interaction energy under extreme conditions. Again, structure changes while constituents remain fundamentally the same. The same pattern appears in high-energy astrophysical processes. When matter is converted into radiation during particle annihilation, mass decreases. When radiation becomes trapped by gravity during collapse, mass increases. General relativity treats all such cases identically because space-time curvature responds to the full energy, momentum content, not to the history of how that energy was assembled. This universality is encoded in the energy-momentum tensor. It includes contributions from rest mass, kinetic energy, pressure, stress, and field energy. Gravitational interaction does not discriminate between Higgs mass, binding energy, or confined radiation. Black holes can form from collapsing stars, from photon shells, or from field-dominated systems. Observations of gravitational waves by LIGO and Virgo confirm that space-time responds only to total energy structure. The implication is direct but carefully bounded. Mass appears whenever energy is constrained in such a way that it defines a stable, frame-invariant structure. This does not imply that energy wants to become mass, nor that mass is a frozen state in a literal sense. It indicates that certain field arrangements prevent energy from dispersing or transforming freely. Experimental demonstrations reinforce this interpretation. Systems of photons can possess invariant mass, even though individual photons do not. When two photons move in opposite directions with equal energy, the system as a whole defines a rest frame. Particle collider experiments routinely exploit this fact when photon collisions produce massive particle pairs. The mass belongs to the configuration, not to the components. What we experience as solidity is therefore not a property of substance, but of stability. Resistance to acceleration arises because changing the motion of a bound field configuration requires rearranging internal energy distributions. That rearrangement demands work. The observed resistance reflects that demand. It remains important to distinguish established conclusions from open questions. While the field-based origin of most hadronic mass is strongly supported by both theory and experiment, the precise relationship between mass and inertia at all scales is still under investigation. Some approaches explore connections between inertia and vacuum field interactions. Others examine emergent behavior in relativistic field systems. No single framework has achieved universal acceptance. What is clear is that mass cannot be reduced to a single mechanism. Higgs coupling explains why some particles can be at rest. QCD confinement explains why most visible matter is heavy. Relativistic field theory explains why configurations, not constituents, determine invariant mass. Gravity responds to all of these without distinction. This layered structure replaces older intuitions without oversimplifying them. Energy does not slow down to become matter. It becomes organized in ways that restrict its freedom. Where that restriction is stable, mass appears. Where it is not, energy remains free to propagate. As experimental tools grow more precise, from collider detectors to space-based observatories, this picture continues to be tested. JWST observations of early galaxies show that massive structures emerged rapidly after the Big Bang, implying efficient mechanisms for trapping energy at large scales. Whether these mechanisms introduce new physics or reflect known field behavior under extreme conditions remains an active area of research. Seen this way, mass is neither illusion nor fundamental ingredient. It is a recurring signature of constrained energy, observed wherever fields form stable, frame-invariant arrangements. That signature appears reliably across laboratory experiments, astrophysical systems, and cosmological observations. Once this framework is accepted, a subtle tension appears. If mass reflects how field systems resist change, then the resistance felt during acceleration cannot come from rest mass alone. It must arise from how entire field configurations respond when they are pushed away from balance. That response is immediate and shared everywhere, suggesting that inertia behaves as an active process, not a fixed property. Part 2. Why didn't the universe stay massless after the Big Bang? There was a time when nothing in the universe could ever stand still, when every form of energy behaved like light, and no particle could claim a place of rest. In the earliest measurable moments after the Big Bang, the universe did not contain mass in the sense we experience it today. According to all available evidence, drawn from particle physics experiments and cosmological observations analyzed by NASA and ESA, the young universe was dominated by radiation. Energy flowed freely through spacetime, and the distinction between massive and massless particles had not yet taken shape. This conclusion does not come from philosophical reconstruction. It comes from converging data. Measurements of the cosmic microwave background by missions such as COBE, WMAP, and later Planck show that, when the universe was about 380,000 years old, it was already cooling from a much hotter, denser state. Particle physics allows us to extrapolate further back, to energies far beyond what any telescope can directly observe. When those extrapolations are combined with accelerator experiments on Earth, a consistent picture emerges. At sufficiently high energies, the laws that distinguish different particle types merge into a more symmetrical form. In that early regime, electromagnetism and the weak nuclear force were not separate interactions. They were unified into what physicists call the electro-weak interaction. More importantly for this story, particles that later would carry mass behaved as if they were massless. They moved at speeds indistinguishable from light and had no preferred state of rest. The universe, in that phase, had no mechanism that allowed energy to settle into durable, resistant forms. The question, then, is not why mass exists today, but why this massless condition did not persist as the universe expanded. Why did a universe that began in a state of pure radiation evolve into one filled with massive particles, atoms, stars, and galaxies? The answer points toward a subtle but decisive change in the structure of fields permeating spacetime. As the universe expanded, its average energy density decreased. This cooling was not uniform in detail, but it followed a clear overall trend confirmed by cosmological models tested against observation. When the temperature of the universe dropped below a critical threshold, roughly corresponding to energies of a few hundred giga-electron-volts, the behavior of one particular field changed dramatically. That field is known as the Higgs field. The Higgs field is not something that appeared suddenly, nor is it something that switched on like a machine. It was present from the beginning as part of the Standard Model's field content. What changed was its state. At very high energies, the Higgs field occupied a symmetric configuration, one that did not single out any particular value across space. In that state, particles interacting with it did not acquire rest mass. As the universe cooled, that symmetric configuration became unstable. This instability is not speculative. It follows directly from the shape of the Higgs field's potential, a mathematical description tested indirectly through particle physics experiments and directly through the properties of the Higgs boson measured at CERN. Below a certain energy, the lowest energy state of the field was no longer the symmetric one. The field settled into a new configuration with a non-zero value everywhere in space. Physicists refer to this transition as electroweak symmetry breaking. Despite the name, it was not an explosion, a rupture, or a localized event. It was a global shift in the lowest energy configuration of a field that already filled the universe. Once this shift occurred, particles that coupled to the Higgs field could no longer behave as pure radiation. Their relationship between energy and motion changed in a precise, measurable way. This is where mass enters the story, but not as a substance that suddenly appeared. Instead, mass emerged as a consequence of interaction. Fields that interacted with the Higgs background found that they could now exist in states where motion could be transformed away by choosing an appropriate reference frame. In practical terms, they could be at rest. That possibility did not exist before the transition. Photons, which do not couple to the Higgs field, remained unchanged. They continued to move at light speed, unaffected by the new background configuration. This contrast, observed and confirmed in countless experiments, makes one point clear. Mass is not a universal attribute imposed on all particles at once. It depends on how specific fields respond to the structure of other fields filling spacetime. Evidence for this process does not come from cosmology alone. High-energy collider experiments recreate conditions similar, in a limited sense, to those that existed shortly after the Big Bang. When particles are smashed together at energies well above their rest masses, the influence of mass diminishes. Behavior begins to resemble that of a massless system. This pattern, repeatedly observed, supports the idea that mass is not fundamental in the highest energy regimes. The Higgs boson itself offers further insight. Its discovery, in 2012, by the ATLAS and CMS collaborations, confirmed the existence of the Higgs field, but its measured mass also raised new questions. The Higgs boson is far lighter than naive theoretical expectations based on quantum corrections. This discrepancy, often discussed under the heading of the hierarchy problem, suggests that the emergence of mass is governed by delicate balances in field behavior rather than by brute necessity. While no definitive explanation has yet been established, the measured values constrain any viable theory. What matters for the early universe is that once electroweak symmetry breaking occurred, the universe could no longer remain entirely massless. Fields that had previously propagated freely now interacted with a persistent background that altered their dynamics. Energy did not slow down. Instead, the rules governing how energy could be arranged changed. This shift had consequences far beyond particle physics. Once particles acquired mass, they could clump. Gravitational attraction, which responds to energy in all its forms, began to act on structures that could remain localized. Density variations, already present at the level of 1 part in 100,000, as revealed by the cosmic microwave background, could grow over time. Without mass, such growth would have been severely limited. Observations by JWST now allow astronomers to see galaxies forming earlier than previously expected. These early structures imply that mass-bearing particles were present and dynamically active well before the universe was 1 billion years old. Their existence traces back, indirectly but reliably, to the electroweak transition. Without that transition, the universe would look profoundly different. Stars, planets, and chemistry, as we know it, would not arise. It is important to note what this explanation does not claim. It does not assert that the Higgs mechanism accounts for all mass in the universe. As explored in the previous part, most of the mass of ordinary matter arises from energy stored in confined fields inside protons and neutrons. The Higgs field explains why certain particles can have rest mass at all, not why composite objects are as heavy as they are. These are complementary pieces of a larger structure. Nor does current science claim to have directly observed the electroweak transition as it occurred in the early universe. What we have instead is a network of consistency. Particle physics experiments, cosmological observations, and theoretical models all point toward the same conclusion. At high energies, mass distinctions disappear. At lower energies, they emerge through well-defined field interactions. NASA has summarized this perspective succinctly in educational material on the early universe, noting that mass arises as the universe cools and its fundamental forces separate. That statement reflects decades of work rather than a single discovery. It also highlights how the appearance of mass is tied to changes in symmetry, not to the introduction of new ingredients. Carl Sagan once remarked, "The cosmos is within us. We are made of star stuff." While often quoted for its poetic resonance, the underlying scientific point is precise. The matter that makes up stars, planets, and living organisms owes its existence to physical processes that occurred when the universe was still young and simple. The emergence of mass was one of those processes governed by the behavior of fields rather than by chance. As the universe continued to expand and cool beyond the electroweak scale, additional transitions followed. Quarks became confined inside hadrons. Electrons bound to nuclei. Atoms formed. Each step added new layers of structure, but none reversed the earlier change that allowed mass to exist in the first place. Once the Higgs field settled into its new configuration, the universe crossed a threshold from which there was no return to complete masslessness. Yet even now, traces of that earlier state remain. Photons still travel without rest. Neutrinos, once thought to be massless, carry only tiny masses, suggesting interactions that differ from those of other particles. These remnants preserve information about conditions that no longer dominate but have not vanished entirely. The deeper implication is cautious rather than declarative. Mass did not appear because the universe aged or because energy lost vigor. It appeared because the underlying fields reorganized themselves as conditions changed. Whether this reorganization was inevitable, or whether alternative field structures could exist under different conditions, remains a subject of active research. As inertia, resistance to acceleration, and interaction with the vacuum come into view, the picture widens. The discussion moves away from how mass first became possible, and toward how it continues to appear each time motion is forced to change. Part 3. Why does the Higgs field make some particles heavy and others invisible to it? One field fills all of space, yet some particles pass through it untouched, while others cannot escape its influence at all. This is not a metaphor, and it is not a simplification. It is a measurable, repeatable fact at the center of modern particle physics, and it defines why light moves forever while matter can stand still. By the late 20th century, physicists had already accepted that the Higgs field exists everywhere. It does not form clouds, currents, or regions of higher density. It does not flow or ripple in any ordinary sense. Instead, it defines a uniform background state of space-time itself. Every laboratory experiment, every accelerator collision, every observation made by detectors on Earth or instruments supported by NASA and ESA is conducted inside this field. Nothing escapes it. And yet, not everything responds to it. This uneven response is not an accident. It is encoded directly into the structure of the Standard Model. Particles do not gain mass simply because they exist within the Higgs field. They gain mass only if their associated fields interact with it in a very specific way. This interaction is known as coupling, and it is neither universal nor optional. Each field either couples to the Higgs field with a defined strength, or it does not couple at all. Electrons do, quarks do, the W and Z bosons do, photons do not. This single distinction explains why light behaves differently from matter. Even though both are described within the same quantum framework, photons are excitations of the electromagnetic field. That field has no coupling to the Higgs background. As a result, the photon's energy and momentum remain locked in a relationship that permits no rest frame. No matter how you move, you cannot transform away a photon's motion. It always propagates at a fixed speed in vacuum, a fact confirmed to extraordinary precision by laboratory experiments and astrophysical observations alike. Electrons behave differently because the electron field couples to the Higgs field. That coupling modifies the electron's energy-momentum relationship. Once the Higgs field settled into its non-zero background state in the early universe, the electron field could no longer behave as a massless excitation. It acquired the ability to exist at rest, and with that ability came inertia and weight. This distinction makes one thing immediately clear. Mass is not something particles possess on their own. It is something that appears only when one field responds to another. Without that response, there is no mass, regardless of how energetic the particle may be. This relational view of mass was not obvious when the Higgs mechanism was first proposed. In the 1960s, when Peter Higgs, François Englert, Robert Brout, and others developed the theoretical framework, the primary goal was not to explain everyday mass. It was to resolve a mathematical inconsistency in the electroweak theory. Without the Higgs field, the equations describing the weak force produced results that violated basic principles of quantum theory. Introducing a background field with specific properties restored consistency. Only later did physicists fully appreciate the broader implication. The same mechanism that preserved mathematical order also explained why some particles are heavy and others are not. The discovery of the Higgs boson in 2012 did not introduce a new idea. It confirmed a structure that had already been tested indirectly for decades. Measurements made at the Large Hadron Collider revealed that the Higgs boson interacts with other particles in proportion to their masses. This was not guaranteed. Alternative models had predicted different patterns. Instead, the observed couplings matched the standard model's expectations within experimental uncertainty. Electrons interacted weakly. Top quarks interacted strongly. Photons did not interact at all. Each result reinforced the same conclusion. Mass tracks interaction strength, not particle identity. This also explains why the Higgs field does not act like a drag force. Particles do not lose energy as they move through it. Electrons moving at constant velocity do not radiate energy simply because they exist in a Higgs background. The field does not resist motion. It alters the structure of permissible states. That distinction is subtle but essential. The Higgs field does not slow particles down. It allows rest to exist. Even the Higgs boson itself fits into this relational picture. The Higgs boson is not massless, but its mass does not arise from coupling to its own background value in the same way electrons do. Instead, the Higgs boson's mass reflects the shape of the Higgs field's potential. That shape determines how much energy is required to excite fluctuations around the background state. In other words, the Higgs boson's mass comes from the internal dynamics of the field, not from an external interaction. This reinforces a broader pattern. Nowhere in the standard model does mass appear as a fundamental substance. It always emerges from structure. It always depends on relationships between fields and the states they occupy. This field-based view also clarifies why mass values differ so dramatically across particles. The electron's mass is about half a mega electron volt. The top quark's mass is roughly 173 giga electron volts. That difference does not reflect size, density, or composition. It reflects coupling strength. The standard model does not currently explain why those couplings take the values they do. They are measured parameters, not derived ones. This limitation is openly acknowledged in the field. NASA educational materials on particle physics emphasize this point carefully, noting that the Higgs mechanism explains how particles get mass, not why those masses have their particular values. That distinction matters. It marks the boundary between established knowledge and open investigation. Photons remain the cleanest counterexample. They carry energy, they carry momentum, they can curve space-time through gravity, and yet they have no rest mass. This combination often appears contradictory at first glance, but it is fully consistent within relativistic field theory. Because the electromagnetic field does not couple to the Higgs field, photons remain locked into a massless dispersion relation. Their behavior is not a special exception. It is a direct consequence of interaction structure. This insight also explains why other particles behave in intermediate ways. Neutrinos, once thought to be massless, are now known to have tiny but non-zero masses. That discovery, confirmed through oscillation experiments and studied by collaborations supported by agencies, including NASA, indicates that neutrinos interact with mass-generating mechanisms beyond the simplest Higgs coupling. Exactly how remains an active area of research. What matters here is that even this exception reinforces the rule. Mass appears only where interaction allows it. The relational nature of mass reshapes how physicists interpret experimental data. In high-energy collisions, when particles are accelerated to energies far exceeding their rest masses, their behavior approaches that of massless fields. Differences between massive and massless particles blur. This convergence is observed routinely in accelerator experiments and aligns with predictions from quantum field theory. At sufficiently high energies, coupling effects become negligible and symmetry is restored. This behavior mirrors conditions in the early universe, as discussed in the previous part. At high temperatures, before the Higgs field settled into its current state, all particles behaved as if they were massless. As the universe cooled, coupling effects became dominant, and mass distinctions emerged. The Higgs field did not impose mass. It revealed which fields were capable of responding to it. Behind these discoveries lies a long history of careful measurement. From early scattering experiments to modern detectors with nanosecond timing resolution, each step refined the picture. The Higgs boson's decay channels, branching ratios, and production rates were scrutinized precisely because they encoded information about coupling strengths. Each confirmed prediction reduced the space of possible alternatives. Carl Sagan often emphasized that science advances by asking what the universe is willing to allow. In this case, the universe allows mass only where interaction supports it. It does not grant mass freely. It ties it to structure, symmetry, and response. This perspective also guards against common misunderstandings. The Higgs field does not explain why objects feel heavy when lifted. That sensation involves inertia and gravity, topics that extend beyond rest mass alone. The Higgs mechanism explains why certain particles can have rest mass at all. It does not account for the majority of the mass of composite objects, nor does it explain resistance to acceleration in full. Those gaps are not failures. They are signposts. They show where one mechanism ends and another begins. They remind us that mass is not a single phenomenon with a single cause. By the time the Higgs field finished reshaping the particle landscape, the universe had acquired the ingredients needed for structure. But structure alone cannot account for how matter resists motion so immediately and so universally. That resistance appears even when gravity plays no role, even when objects are isolated from everything except carefully applied forces. At that point, rest mass no longer tells the full story. What comes into view instead is inertia itself, emerging from how accelerating systems interact with the surrounding fields in ways that cannot be set aside. Part 4. Why is the mass of ordinary matter mostly not from the Higgs at all? Nearly all of the mass you feel when you lift an object does not come from the mechanism that first made mass possible. This statement sounds wrong at first hearing, yet it is supported by some of the most precise measurements ever made in particle physics. If the Higgs field gives mass to fundamental particles, then a simple expectation follows naturally. Objects built from those particles should owe most of their mass to the Higgs as well. But protons and neutrons do not follow that expectation. Their mass comes from somewhere else entirely. A proton has a mass of about 938 mega-electronvolts when expressed as energy. If one adds together the Higgs-generated masses of its constituent quarks, the total reaches only a few tens of mega-electronvolts. That gap is not a rounding error. It represents more than 90% of the proton's mass. The same is true for neutrons. The matter that makes up planets, stars, and human bodies is therefore overwhelmingly heavy for reasons unrelated to the Higgs field. This conclusion was not obvious when quarks were first proposed. In the 1960s, when experiments at the Stanford Linear Accelerator Center began probing the internal structure of protons using high-energy electrons, physicists expected to find something like small, solid constituents carrying most of the mass. Instead, the data revealed a far more dynamic picture. The scattering patterns showed that quarks behave almost as if they were free when struck hard enough, yet they are never observed in isolation. The proton did not appear to be a static assembly. It behaved like a restless system of fields. This behavior led to the development of quantum chromodynamics, the theory describing the strong interaction. In this theory, quarks carry a property known as color charge, and they interact by exchanging gluons. Gluons themselves are massless, but they carry color charge and interact strongly with one another. This self-interaction sets the strong force apart from electromagnetism and gives rise to confinement. Confinement means that quarks and gluons cannot spread out freely. As they attempt to separate, the energy stored in the gluon field between them increases. Unlike the electromagnetic field, which weakens with distance, the strong field resists separation more intensely, the farther quarks are pulled apart. Eventually, it becomes energetically favorable to create new quark-antiquark pairs rather than allow isolation. As a result, free quarks are never observed. This confinement has a profound consequence for mass. Inside a proton, quarks move at speeds approaching that of light. Gluons continually form, interact, and dissolve. The system is dominated not by the rest masses of the quarks, but by their kinetic energy, and by the energy stored in the gluon fields that bind them together. According to relativity, any energy that remains within a system and cannot be transformed away contributes to that system's mass. The proton satisfies this condition exactly. Experimental evidence for this picture accumulated gradually. Deep inelastic scattering experiments revealed that gluons carry a large fraction of the proton's momentum. Later measurements at particle colliders refined this result, showing that gluons dominate the internal dynamics even at moderate energies. Lattice quantum chromodynamics, a computational approach that simulates the theory on a discrete spacetime grid, reproduced the proton's mass from first principles. These simulations did not rely on heavy quark masses. They relied on field energy under confinement. This success marked a turning point. It showed that mass can emerge as a collective effect without being assigned to individual constituents. The proton's mass is not stored in its parts like weight in a container. It arises from the total energy of a bound field system. NASA and ESA materials on fundamental physics reflect this understanding carefully. They emphasize that ordinary matter is heavy because of the strong force, not because of the Higgs field. The Higgs field explains why quarks can have rest mass at all, but it does not explain why protons are as heavy as they are. That explanation lies in how the strong interaction organizes energy. The story becomes even clearer when one considers thought experiments supported by real data. Imagine a universe in which the Higgs field still operates, giving quarks small rest masses, but the strong interaction does not confine them. In such a universe, quarks would move freely like electrons in a plasma. Bound nucleons would not exist. The mass of any composite object would be far smaller than what we observe. Chemistry, nuclei, and stable matter would be impossible. Conversely, imagine a universe in which quarks were massless, but confinement still occurred. Calculations and simulations suggest that protons would still possess most of their present mass. The strong force would still trap energy into localized structures. That trapped energy would still appear as mass. This comparison highlights where the dominant contribution truly lies. The idea that mass can arise without heavy constituents reshaped how physicists interpret matter at all scales. In neutron stars, where densities exceed that of atomic nuclei, matter is compressed into extreme states governed by strong interactions. Observations made by NASA's NICA mission constrain the equation of state of such matter. These constraints show that pressure and interaction energy contribute significantly to the star's mass energy content. Again, the mass does not originate from Higgs coupling alone. Even in the early universe, before protons formed, similar principles applied. As quarks cooled and became confined into hadrons, a large amount of mass energy appeared in a short span of cosmic time. This transition did not require new particles. It required a change in how existing fields organized themselves. The universe did not gain weight by adding ingredients. It gained weight by rearranging energy into bound configurations. The history behind this understanding is itself instructive. In the early development of quantum chromodynamics, many physicists doubted whether such a strongly interacting theory could ever yield precise predictions. The equations resisted analytic solutions. Progress depended on advances in computation and on experimental patience. Decades passed between the first hints of quark confinement and the numerical confirmation of hadron masses from lattice calculations. The result was not a dramatic revelation, but a quiet convergence of theory and data. One of the most concise summaries of this outcome came from Frank Wilczek, who stated, "Most of the mass of ordinary matter comes from the energy of gluons." This sentence is often repeated because it captures the core result without exaggeration. It does not diminish the role of the Higgs field. It places it in context. This context matters because it prevents a common misunderstanding. The Higgs field is sometimes described in popular accounts as the source of all mass. That description is incomplete. The Higgs field determines which fundamental particles can possess rest mass. It does not determine how heavy composite objects become once strong interactions dominate. Confusing these roles obscures the layered structure of physical explanation. In practical terms, when you hold an object, you are feeling the inertia of confined energy. You are interacting with a system whose resistance to acceleration comes from the need to rearrange a dense network of gluon fields and rapidly moving quarks. That resistance is real, measurable, and reproducible. It does not depend on the historical path by which the energy entered the system. This perspective aligns naturally with relativity. Mass is a measure of energy content that remains invariant under changes of reference frame. In a proton, the internal energy cannot be eliminated by boosting to another frame. It is locked in place by confinement. As long as that confinement holds, the mass persists. While quantum chromodynamics successfully accounts for hadron masses, the detailed behavior of strongly interacting matter under all conditions is still under active study. High-density phases, such as quark, gluon plasma, and possible exotic states inside neutron stars, challenge existing models. Observations from heavy ion collisions and astrophysical measurements continue to refine the picture. The mass of ordinary matter is not a sum of fundamental masses. It is an emergent property of interacting fields. It arises dynamically from energy that cannot escape a bound configuration. This emergence is not speculative. It is grounded in experiment, computation, and observation across many domains of physics. If mass is largely a collective effect of confined energy, then the resistance felt during acceleration cannot be explained by simply adding up the masses of individual components. It must arise from how entire field configurations respond when motion is forced to change. In that response, inertia comes into view, revealing another way mass expresses itself beyond what the Higgs alone accounts for. Part 5. Why is Higgs mass not the same as the mass we feel when we push an object? You can explain why a particle is allowed to stand still and still have no explanation at all for why it resists being pushed. That gap is real, measurable, and deeply embedded in physics. The Higgs field tells us which particles may possess rest mass, but the moment you place your hand on an object and try to accelerate it, you encounter something else entirely. The resistance you feel does not arise simply because the object has mass. It arises because changing motion forces an entire system of fields to respond. This distinction became unavoidable once the Higgs mechanism was confirmed. After the discovery of the Higgs boson in 2012, it was tempting to treat the problem of mass as solved. Yet even the most careful summaries from NASA and CERN made an important clarification. The Higgs field explains rest mass. It does not by itself explain inertia. These two ideas are related, but they are not the same phenomenon. Rest mass describes whether a particle can exist in a frame where it is not moving. Inertial mass describes how strongly a system resists acceleration when a force is applied. In everyday experience, these appear inseparable, because objects that can rest also resist motion. But physics shows that the link is not automatic. The Higgs field determines the first property. The second emerges only when motion is changed. This separation was already implicit in classical mechanics. Isaac Newton defined mass operationally through resistance to acceleration. He did not describe mass as substance, but as response. Yet Newton's framework could not explain why that response existed. It merely described how it behaved. With the development of relativity and quantum field theory, the question sharpened. If mass comes from Higgs coupling, why does that coupling not directly explain inertia? The answer begins with recognizing what acceleration means in field theory. To accelerate an object is not simply to change the trajectory of a point. It is to force every field configuration inside that object to reorganize. In a proton, that includes quarks moving at relativistic speeds and gluon fields under constant tension. In an atom, it includes electromagnetic fields binding electrons to nuclei. In a solid object, it includes collective excitations across billions of interacting particles. Acceleration disturbs all of them at once. This disturbance carries an energetic cost. Fields resist being reshaped rapidly. That resistance appears as inertia. The effect is immediate, not because something mysterious acts instantaneously, but because field interactions propagate within the object at speeds far exceeding the scale of the applied force. The system responds as a whole. Crucially, the Higgs field does not participate in this response in the same way. The Higgs field sets the background condition that allows rest to exist. It does not supply the energy stored in confined gluon fields, nor does it govern the rearrangement of electromagnetic binding energy under acceleration. When you push an object, you are not pushing against the Higgs field. You are pushing against the internal dynamics of interacting fields. This insight became clearer as quantum chromodynamics matured. As discussed in the previous part, most of the mass of ordinary matter arises from confined field energy inside protons and neutrons. That same confined energy must be rearranged when motion changes. The stronger the confinement, the greater the resistance. Inertia, in this view, reflects the cost of reorganizing bound energy under acceleration. Experimental evidence supports this interpretation indirectly but consistently. In high-energy particle collisions, where particles are accelerated to extreme energies, their inertial behavior depends on the total energy of the system, not merely on Higgs-generated rest mass. Systems with identical rest mass but different internal energy distributions respond differently under applied forces. These differences vanish only when internal structure becomes irrelevant at extreme energies. Relativity reinforces the point. In special relativity, the resistance to acceleration increases with energy. This is not because mass increases in a material sense, but because the system's energy content resists further change in motion. The equations describe how force couples to energy and momentum, not to substance. Inertia tracks energy distribution. NASA educational materials on relativity emphasize that mass and energy are inseparable in dynamical contexts. An object with higher internal energy resists acceleration more strongly, even if its constituent particles have the same rest masses. This is why heating an object increases its inertial mass by a tiny but measurable amount, a result confirmed in precision experiments. These experiments reveal something subtle. Inertia is not stored in particles like a property label. It emerges when fields interact and are forced out of equilibrium. The resistance appears only when change is imposed. At rest, the system reveals no inertial behavior. Under uniform motion, none appears either. Only acceleration brings it into view. This explains why the Higgs mechanism cannot account for inertia alone. The Higgs field does not determine how fields react when motion changes. It determines which fields are allowed to define rest. The response to acceleration belongs to the interactions within the system, not to the background field that permits rest in the first place. Historical context makes this distinction sharper. In the early 20th century, physicists debated whether inertial mass and gravitational mass were truly equivalent or merely numerically similar. Experiments refined by Vos, and later by modern space-based tests supported by ESA, showed equivalence to extraordinary precision. General relativity incorporated this equivalence, by tying gravity to energy momentum rather than mass alone. Yet even within relativity, inertia remains a dynamical response. Space-time curvature influences motion, but resistance to acceleration arises locally from the energy content of fields. Gravity does not create inertia, it responds to it. This layered picture avoids oversimplification. Higgs coupling explains why particles can be at rest. Quantum chromodynamics explains why protons are heavy. Field dynamics explain why systems resist acceleration. Each mechanism operates at a different level. None replaces the others. It is important to note what remains unresolved. While field-based explanations of inertia are consistent with known physics, no single formulation has been universally accepted as complete. Some approaches explore how accelerating systems interact with vacuum fields. Others examine emergent inertia in relativistic many-body systems. These ideas are constrained by experiment, but not yet fully unified. What is firmly established is the separation itself. Rest mass and inertial mass coincide numerically under ordinary conditions, but they arise from different physical processes. Treating them as identical obscures the richness of the underlying physics. Carl Sagan often reminded audiences that understanding deepens when familiar ideas are re-examined under new light. Here, the familiar sensation of pushing an object reveals layers of structure beneath it. The resistance you feel is not the Higgs field pushing back. It is the collective response of energy arranged in stable configurations, resisting being reshaped. This realization carries a quiet implication. If inertia is a response rather than a property, then it must involve interaction with something beyond the object itself. The object does not resist acceleration in isolation. It resists because changing its motion alters its relationship with surrounding fields. That interaction does not remain confined to the object alone. It extends outward, into the vacuum itself, where resistance begins to appear not as a built-in property, but as a response that emerges during motion. Part 6. Why does inertia feel like a reaction rather than a property? The moment you apply a force to matter, resistance appears immediately, with no delay and no build-up, as if something outside the object has answered your action at once. This immediacy is not an illusion of perception. It is a reproducible physical fact that has been tested across scales, from laboratory experiments to spacecraft dynamics monitored by NASA and ESA. Inertia does not wait, it responds. And that behavior alone already suggests that inertia is not stored quietly inside particles like a passive label, but arises from an active physical process that unfolds as motion is forced to change. Classical mechanics described inertia with great success but little explanation. Newton defined it operationally, not structurally. Mass measured resistance to acceleration, and the laws worked. But they did not reveal where that resistance came from. For centuries, inertia was treated as an intrinsic property of matter, something objects simply possessed. That view became increasingly difficult to maintain as physics moved from particles to fields. Once matter was understood as configurations of interacting fields, the instantaneous character of inertial resistance took on new significance. Fields are not static objects. They are extended systems defined everywhere in space and time. When an object accelerates, the fields that constitute it cannot all adjust at once without consequence. They must reorganize, redistribute energy, and maintain internal consistency. That reorganization is not free. In quantum field theory, every particle is an excitation of an underlying field. In composite matter, such as atoms and solids, countless fields are coupled together. Electromagnetic fields bind electrons to nuclei. Strong interaction fields confine quarks inside protons and neutrons. These interactions create stable configurations that persist over time. When acceleration is imposed, the entire configuration is disturbed. The system is forced away from equilibrium. The resistance that emerges reflects the energetic cost of this disturbance. Fields resist rapid change. This is not a metaphor. It is encoded in the equations governing their dynamics. Sudden acceleration requires energy to be redistributed across interacting degrees of freedom. The more tightly bound and energetic the configuration, the greater the resistance. This perspective explains why inertia scales with total energy content rather than with the Higgs-generated masses of individual particles. As established in earlier parts, most of the mass of ordinary matter comes from confined field energy, particularly from quantum chromodynamics. Those same confined fields dominate inertial behavior. Accelerating an object means accelerating a dense network of interacting fields whose internal motions must remain consistent with one another. Experimental evidence supports this view in subtle but compelling ways. Precision tests of special relativity show that as an object's internal energy increases, its resistance to acceleration increases correspondingly. Heating an object raises its inertial mass by a small but measurable amount. This effect has been confirmed in high-precision experiments and is consistent with relativistic predictions. The increase does not depend on changes in Higgs coupling. It depends on added internal energy. Particle accelerator experiments provide another window. When composite particles are accelerated to extreme energies, their inertial response reflects not just their rest mass, but their full energy content. Systems with identical rest masses but different internal excitation states behave differently under acceleration. These differences disappear only when internal structure becomes irrelevant at sufficiently high energies, where all behavior approaches that of nearly massless fields. The immediacy of inertial response is also revealing. There is no observable lag between applied force and resistance. This does not imply instantaneous action at a distance. It reflects the fact that field interactions within matter operate on timescales far shorter than those of macroscopic motion. The rearrangement of field configurations happens at speeds governed by fundamental interactions, many orders of magnitude faster than any mechanical motion we can observe. This understanding reshaped how physicists interpret inertia. Rather than viewing it as a static attribute, it is increasingly treated as a dynamical response. Inertia appears when acceleration forces fields out of equilibrium. It disappears when motion is uniform. At rest, or at constant velocity, no inertial resistance manifests. Only change in motion reveals it. Historical context adds depth to this picture. In the early 20th century, Ernst Mach proposed that inertia might arise from interaction with the rest of the universe. While Mach's ideas were never fully formalized into a complete theory, they influenced Einstein's thinking as he developed general relativity. Einstein ultimately tied gravity to space-time curvature rather than to distant matter directly, but the question of inertia's deeper origin remained open. General relativity treats inertia and gravity within a unified geometric framework, yet it does not reduce inertia to geometry alone. In curved spacetime, free-falling objects follow geodesics without resistance. Inertia appears only when deviation from those paths is enforced. Once again, resistance emerges when motion is constrained or altered, not when it proceeds freely. Modern research explores inertia from several complementary angles. Some approaches examine how accelerating systems interact with vacuum fields. Others focus on emergent behavior in many body field systems. None of these approaches has yet achieved complete consensus, but all share a common theme. Inertia is not an isolated property residing inside particles. It arises from interaction. NASA-supported experiments on precision measurement, along with ESA missions testing fundamental physics in space, continue to refine constraints on inertial behavior. These experiments consistently support energy-based descriptions. No deviation has been observed that would suggest inertia exists independently of field interactions. One of the most striking features of inertial resistance is its universality. It does not depend on composition, shape, or internal arrangement in any simple way. Objects made of different materials resist acceleration in proportion to their total mass energy. This universality is precisely what one would expect if inertia reflects a general response of fields to acceleration, rather than a property tied to specific particles. This view also clarifies why inertia feels external. When you push an object, the resistance does not seem to come from within your hand or from a particular point inside the object. It feels as if the object as a whole pushes back. That sensation corresponds to a physical reality. The entire field configuration responds collectively. There is no localized source of inertia. It is distributed across the interacting system. It is important to be precise about what is established and what remains open. Physics has not yet produced a single, complete theory that derives inertia from first principles in all contexts. What exists instead is a converging body of evidence indicating that inertia behaves like a reaction rather than a stored quantity. Field dynamics, energy redistribution, and interaction strength all play central roles. Carl Sagan often emphasized that understanding deepens when we replace familiar labels with mechanisms. Calling inertia a property explains nothing. Describing it as a response grounded in field behavior brings us closer to physical understanding, even if the final formulation remains incomplete. This shift in perspective also guards against oversimplification. Inertia is not caused by the Higgs field. It is not caused by gravity. It is not caused by a single interaction. It emerges from how energy, arranged in stable configurations, resists being reorganized too quickly. Seen this way, inertia becomes less mysterious and more demanding. It requires accounting for every interaction that holds matter together. It demands attention to fields we do not see, but can measure indirectly. It insists that resistance to motion is not a primitive fact, but a consequence of structure. As research continues, this field-based view of inertia connects naturally to deeper questions about the vacuum itself. If fields resist change, and if fields fill all of space even in their lowest energy states, then acceleration may involve interaction with more than just the matter being accelerated. The vacuum cannot remain entirely passive. That realization reaches beyond matter itself. It begins to involve the structure of empty space, where inertia no longer appears as something tied only to objects, but as a response shaped by the vacuum around them. Part 7. Why does the vacuum refuse to be truly empty? Even when every particle is removed, every atom stripped away, and every measurable trace of matter eliminated, something still remains, and it refuses to disappear. This is not a philosophical statement or a speculative idea. It is a result confirmed repeatedly by experiment, and it forces physics to abandon the comforting notion that empty space can ever be truly empty. In classical physics, a vacuum was imagined as a perfect void. Remove all matter, and nothing should be left behind. This picture worked well enough for centuries, until experiments became precise enough to probe what happens when space is pushed to its quietest possible state. What emerged from those experiments was not silence, but structure. Quantum field theory begins with a simple but demanding premise. Every fundamental field exists everywhere in space, not only where particles are present. Fields cannot be switched off. A particle is not the field itself, but an excitation of that field. Removing the excitation does not remove the field. It leaves the field in its lowest energy configuration, a state known as the vacuum. That lowest energy state is not featureless. The uncertainty principle forbids a field from having both perfectly defined strength and perfectly defined rate of change at the same time. As a result, even in the vacuum state, fields exhibit fluctuations. These fluctuations do not represent particles popping in and out of existence in a literal sense, but measurable variations in field values that cannot be eliminated. This is not inferred indirectly. It is observed. One of the earliest clues came from atomic physics. In spontaneous emission, an excited atom emits a photon even when no external electromagnetic radiation is present. Classical theory offered no satisfactory explanation. If the vacuum were truly empty, nothing should trigger the emission. Quantum electrodynamics resolved this by recognizing that the electromagnetic field in vacuum still fluctuates. Those fluctuations interact with the atom and provide a pathway for emission. The vacuum does not merely permit the process, it participates in it. Another decisive demonstration came from the Casimir effect. In 1948, Hendrik Casimir predicted that two uncharged parallel metal plates placed extremely close together in vacuum would experience an attractive force. This force would not arise from electromagnetism in the usual sense, but from the modification of vacuum field modes between the plates. Certain fluctuations would be suppressed between the plates while remaining allowed outside, creating a measurable pressure difference. Decades later, experiments confirmed Casimir's prediction with increasing precision. Modern measurements, conducted with nanometer-scale separations, show forces exactly consistent with quantum vacuum calculations. No particles are exchanged. No hidden charges are involved. The effect arises purely from the structure of the vacuum itself. These results leave little room for ambiguity. The vacuum has physical properties. It carries energy. It responds to boundaries. It influences matter. This realization reshaped how physicists think about motion and acceleration. If fields fill space even in their lowest energy states, then accelerating matter cannot avoid interacting with them. Acceleration is not merely a change in trajectory. It is a change in how a system moves relative to a background of fields that are always present. The idea that the vacuum might influence inertial behavior is not new. It has appeared in various forms throughout the 20th century. What changed was the experimental grounding. As quantum field theory matured, the vacuum stopped being a mathematical convenience and became a physical entity with measurable effects. NASA and ESA research programs dealing with precision measurement, atomic clocks, and space-based experiments have repeatedly had to account for vacuum fluctuations. Atomic transition rates, noise flaws in detectors, and limits on measurement precision are all influenced by vacuum field behavior. These are not speculative corrections. They are required for agreement between theory and observation. At the same time, astrophysical observations reinforce the same lesson. Processes near black holes, neutron stars, and in the early universe cannot be modeled accurately without accounting for quantum fields in their vacuum states. Hawking radiation, predicted from quantum field behavior near event horizons, depends critically on vacuum fluctuations. While direct detection remains challenging, indirect evidence continues to support the framework. The vacuum also plays a role in cosmology. Measurements of the universe's expansion indicate the presence of a small but non-zero energy density associated with empty space itself. This energy, often referred to as dark energy, is distinct from the zero-point energies of quantum fields, and its precise origin remains unresolved. What matters here is that even on the largest scales, empty space contributes dynamically to the behavior of the universe. Returning to inertia, the implications become difficult to ignore. If an object accelerates through space filled with structured fields, then part of its resistance may arise from interaction with that background. This does not mean the vacuum acts like a fluid or exerts a drag force. Experiments show no such effect under uniform motion. But acceleration changes the relationship between matter and the surrounding fields, and that change carries energetic consequences. In quantum field theory, accelerated observers perceive the vacuum differently from inertial observers. This is not a matter of opinion or interpretation. It is a mathematically precise result. An observer undergoing constant acceleration detects a thermal spectrum of excitations in the vacuum, a phenomenon known as the Unruh effect. While extremely difficult to observe directly because the accelerations required are enormous, the effect is a robust prediction of established theory. The Unruh effect illustrates a crucial point. The vacuum is not an absolute state independent of motion. Its properties depend on how it is probed. What appears as empty space to one observer can appear as a bath of excitations to another. This observer dependence does not violate physical laws. It reveals that the vacuum is an active participant in physical processes. These ideas remain under active investigation. No experiment has yet demonstrated a direct causal link between vacuum fluctuations and inertia itself. Physics does not claim that inertia has been fully derived from vacuum interactions. What exists instead is a growing body of evidence showing that the vacuum cannot be ignored when motion changes. The resistance encountered during acceleration may reflect not only the rearrangement of internal fields within matter, but also the adjustment of those fields relative to a pervasive background. In this view, inertia becomes a relational phenomenon, emerging from interactions that extend beyond the boundaries of the object. Historical perspective adds depth here. Early in the development of quantum electrodynamics, physicists were uncomfortable with the idea that empty space could carry infinite energy. Renormalization techniques were developed to handle these infinities, allowing precise predictions without assigning direct physical meaning to absolute vacuum energy. Yet the measurable effects remained. The Casimir force did not vanish. Spontaneous emission did not disappear. As experimental precision improved, the vacuum asserted itself more clearly. It could be shaped by boundaries, it could influence decay rates, it could contribute to observable forces. Empty space was not a backdrop, it was part of the system. Carl Sagan often emphasized that the universe is not obligated to conform to human intuition. The quantum vacuum is a prime example. It contradicts the everyday idea of emptiness, yet it does so in a disciplined, testable way. Every claim about the vacuum that has survived experimental scrutiny has done so because it produces numbers that match observation. It is essential to be careful about what is known and what is not. Physics does not assert that vacuum fluctuations alone cause inertia, nor does it claim that zero-point energy explains all resistance to acceleration. These remain open questions. What is firmly established is that the vacuum has structure, and that this structure interacts with matter under changing conditions. That interaction places constraints on any complete theory of inertia. A theory that treats inertia as a purely internal property of matter, isolated from the vacuum, must explain why vacuum fluctuations affect atomic behavior, force measurements, and field dynamics so consistently. No such explanation has yet succeeded. What remains is a picture of increasing coherence. Matter is made of fields. Fields fill space. Even in their lowest energy states, those fields fluctuate and respond. When matter accelerates, it cannot help but interact with this environment. Resistance emerges not from isolation, but from relationship. This perspective does not simplify the problem of inertia, it deepens it. It ties resistance to motion to the structure of space itself, not as a metaphor, but as a physical requirement imposed by quantum field theory. And once the vacuum is recognized as active rather than passive, another consequence follows naturally. If energy configurations, whether in matter or in empty space, can contribute to inertia and gravity, then mass itself may appear in situations where no massive particles are present at all. That possibility does not stop at matter or vacuum alone. It extends to light itself, where energy by itself can give rise to mass, and the boundary between substance and structure begins to lose its clarity. Part 8. Why can light create mass without ever having it? Light is defined, from the very beginning of modern physics, as something that cannot stand still. A photon has no rest frame. No matter how fast you move, you will never catch up to it. This is not an assumption. It is a direct consequence of special relativity, confirmed by every precision test ever performed. And yet, under carefully arranged conditions, light can give rise to mass. Not metaphorical mass. Not effective mass. Real, invariant mass that behaves exactly like the mass of ordinary matter. That fact forces a deep rethinking of what mass actually measures. A single photon carries energy and momentum, but it has zero rest mass. This statement is precise. It does not mean the photon is weightless in a gravitational sense. General relativity shows that light curves space-time and responds to gravity. But rest mass is defined differently. It is the mass measured in a frame where the total momentum of a system is zero. For an individual photon, such a frame does not exist. Its motion cannot be transformed away. The surprise appears when photons are considered not individually, but as a system. Take two photons with equal energy moving in opposite directions. Each photon alone has no rest mass, yet together the system does. There exists a frame in which the total momentum cancels out. In that frame, the system is at rest. The energy present in that configuration cannot be removed by changing reference frames, and according to relativity, that energy corresponds to an invariant mass. This is not a theoretical curiosity. It is a routinely used concept in particle physics. In high-energy experiments, photons collide and produce massive particle pairs. The mass of the produced particles does not come from hidden ingredients. It comes from the energy of the photons arranged in a configuration that admits a rest frame. What matters here is not the nature of the constituents, but the structure of the system. Relativity makes this distinction unavoidable. Mass is not defined by what something is made of. It is defined by how energy and momentum are distributed. When energy flows freely in one direction, as with a single photon, no rest frame exists, and no invariant mass can be assigned. When energy is arranged so that motion cancels internally, mass appears. This principle was understood soon after Einstein developed special relativity, but its implications were easy to overlook. Early discussions of mass often focused on particles as objects. As quantum field theory matured, it became clear that particles are excitations, and that systems of excitations obey rules that cannot be reduced to their individual components. Experiments at particle accelerators have made this concrete. Two photons produced in opposite directions during electron-positron annihilation form a system with zero invariant mass because their energies balance perfectly. Change the geometry slightly, alter the angles or energies, and the invariant mass of the photon system changes. This invariant mass determines which particles can be produced in subsequent interactions. Physicists do not treat this as an analogy. They calculate it. They measure it. Detectors at CERN, supported by agencies including NASA and ESA through collaborative research, rely on invariant mass reconstruction as a primary tool. When a particle decays into photons, its mass is inferred from the combined energy and directions of those photons. The photon system carries the mass signature of the parent particle. This alone shows that mass is not a property glued onto particles. It is a property of configurations. The distinction between rest mass and what was once called relativistic mass is important here. Modern physics avoids the term relativistic mass because it obscures the underlying structure. What increases with energy is not mass in the invariant sense, but resistance to acceleration. Invariant mass remains tied to the existence of a rest frame for the system as a whole. Light can participate in that structure. It simply cannot do so alone. Astrophysical observations reinforce the same conclusion. In regions of intense radiation density, such as the early universe or the interiors of stars, radiation contributes significantly to gravitational dynamics. In the early universe, before matter dominated, radiation shaped the expansion rate. The cosmic microwave background, measured by missions such as Planck, preserves evidence of this radiation-dominated era. During that time, energy density, not particle rest mass, governed gravitational behavior. General relativity does not distinguish between mass and energy as sources of gravity. Both contribute through the energy-momentum tensor, a dense configuration of radiation curves spacetime just as matter does. In principle, a sufficiently intense photon configuration could collapse into a black hole. This is not speculative. It follows directly from Einstein's equations. This possibility underscores the core idea. Mass is not a substance added to energy. It is a measure of how energy is organized. The story becomes even more striking when pair production is considered. When a high-energy photon passes near a nucleus, it can transform into an electron-positron pair. The photon did not carry rest mass before the interaction. Afterward, two massive particles exist. Conservation laws are not violated. Energy and momentum are redistributed. The presence of the nucleus allows momentum to be conserved, while a rest frame for the produced system becomes possible. The mass of the electron and positron is not created from nothing. It emerges from the photon's energy once the configuration allows it. This process has been observed countless times. It is one of the earliest confirmations of mass-energy equivalence. Yet, its deeper lesson is often missed. The photon did not turn into mass because it slowed down. It turned into mass because the interaction allowed energy to be arranged into a configuration with a rest frame. That lesson applies broadly. It applies to hadrons, whose mass arises from confined field energy. It applies to inertia, which arises from resistance to rearranging energy. And it applies to light, which can contribute to mass without ever possessing it intrinsically. NASA educational materials on relativity emphasize that mass is a property of systems, not just particles. This framing avoids confusion and aligns with how modern experiments operate. When detectors measure mass, they measure the invariant mass of final state systems, reconstructed from energy and momentum data. This perspective also resolves apparent paradoxes. Light is massless, yet it has weight in a gravitational field. Light cannot be at rest, yet it can form systems that are. These statements do not contradict one another, they reflect different levels of description. The invariant mass of a system depends on whether internal motion can be transformed away. Two photons moving in opposite directions have internal motion but no net motion. The energy remains, the momentum cancels, and mass appears. This insight reshapes how physicists interpret the boundary between matter and radiation. The boundary is not sharp, it depends on configuration. Matter can behave like radiation at high energies. Radiation can behave like matter when trapped or arranged symmetrically. In cosmology, this fluidity mattered enormously. During the early universe, radiation energy density determined the expansion rate. As the universe expanded and cooled, matter energy density took over. The transition did not involve a change in fundamental ingredients, but a change in how energy was distributed and diluted with expansion. JWST observations of early galaxies now provide evidence that massive structures formed earlier than once thought. Those structures required configurations in which energy could settle into bound systems. Light alone cannot form such structures unless it is confined. Matter provided the necessary mechanisms, but the underlying principle remains the same. Mass follows configuration. It is important to remain precise about what is established and what is not. Physics does not claim that mass can always be generated from light alone under arbitrary conditions. Constraints of momentum conservation, interaction cross-sections, and available energy apply. What is established is that no massive constituent is required in principle. Energy arranged appropriately is sufficient. This conclusion does not diminish the role of the Higgs field. The Higgs mechanism explains why certain particles can possess rest mass individually. The photon lacks that coupling and remains massless. But the Higgs mechanism does not govern system-level mass. That emerges from relativistic structure. Carl Sagan often emphasized that the universe reveals its rules through consistency rather than spectacle. The ability of light to give rise to mass without ever having it is one such rule. It is not dramatic when first stated. It becomes profound only when followed carefully to its implications. Those implications point toward a view of mass as a bookkeeping quantity for energy that cannot be transformed away. Wherever energy is trapped, balanced, or symmetrically arranged, mass appears. Wherever it is free to stream unidirectionally, it does not. If gravity responds equally to all forms of energy, and if mass can arise from configurations rather than constituents, then how mass is assembled no longer matters. Gravity reacts the same way regardless of whether mass comes from particles, fields, or confined energy. In that behavior, gravity appears not as something tied to matter itself, but as a response to energy in every form it can take. Part 9. Why doesn't gravity care how mass is created? Gravity does something unsettlingly simple. It pulls on everything that carries energy, without asking where that energy came from. Whether mass arises from the Higgs field, from the tension of gluon fields inside protons, from tightly packed radiation, or even from the structured vacuum itself, gravity responds in exactly the same way. This indifference is not a poetic idea. It is a rigorously tested feature of nature, and it stands at the center of modern gravitational physics. Before the 20th century, gravity was often thought of as a force between masses. Heavier objects pulled more strongly, lighter objects pulled less. This view worked well for planets and apples, but it quietly hid an assumption. It assumed that mass was a single, well-defined substance. As physics uncovered multiple ways for mass to arise, that assumption became impossible to maintain. The turning point came with Einstein's general theory of relativity. In this framework, gravity is no longer a force acting between objects. It is a manifestation of space-time curvature. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Crucially, the source of this curvature is not mass alone. It is the full energy, momentum content of a system. This distinction matters. Energy, momentum includes rest mass, kinetic energy, pressure, stress, radiation, and even contributions from quantum fields in their lowest energy states. Gravity responds to all of it. No term in Einstein's equation singles out Higgs-generated mass as special. No preference is given to mass that comes from confined gluons or from electromagnetic binding energy. To gravity, these distinctions do not exist. This universality was not assumed. It was tested. Early clues appeared in the equivalence principle, the observation that gravitational mass and inertial mass are proportional with extraordinary precision. Experiments refined over the 20th century, including torsion balance tests and later space-based measurements supported by ESA, showed that objects with very different compositions fall at the same rate in a gravitational field. Materials dominated by nuclear binding energy fall, just like those dominated by electromagnetic energy. Gravity does not discriminate. General relativity extends this result beyond matter. Light bends in a gravitational field. This was confirmed dramatically during the solar eclipse of 1919, when starlight passing near the Sun was observed to deflect by exactly the amount predicted by Einstein's theory. Light has no rest mass, yet it gravitates. This alone shows that gravity cannot be responding to mass in the narrow sense. Modern observations reinforce the same lesson. Gravitational lensing measured by NASA and ESA missions shows that entire galaxies bend light, revealing mass distributions that include visible matter, dark matter, and energy stored in fields. The lensing depends only on total energy content. It does not reveal how that energy is packaged. Black holes provide the most extreme confirmation of this principle. A black hole does not remember how it formed. Whether it arises from the collapse of a massive star, from the merger of neutron stars, or from an intense concentration of radiation, its gravitational field is determined solely by a small set of quantities: mass energy, angular momentum, and electric charge. The origin of that mass energy is erased from the external description. This is not an interpretive statement. It follows from exact solutions of Einstein's equations. Once a black hole forms, all detailed information about the internal composition becomes inaccessible. Gravity responds only to the total energy that remains trapped behind the event horizon. The possibility of forming black holes from light alone follows directly from this logic. If enough radiation is compressed into a sufficiently small region, space-time curvature becomes strong enough to trap that radiation. No massive particles are required in principle. While such conditions are extreme and not easily realized in nature, the equations allow them. Gravity does not require mass in the particle sense. It requires energy that cannot escape. Astrophysical observations of the early universe support this energy-based view. During the radiation-dominated era, long before atoms or stars existed, the expansion rate of the universe was governed primarily by radiation energy density. The cosmic microwave background, measured with exquisite precision by missions such as Planck, preserves signatures of this phase. The imprint of acoustic oscillations reflects a universe where photons played a central gravitational role. As the universe expanded and cooled, matter began to dominate the energy budget. But gravity itself did not change its rules. It responded continuously to whatever form of energy was present. The transition from radiation domination to matter domination altered cosmic evolution, not because gravity changed, but because the composition of energy did. This continuity explains why gravity appears so indifferent to microscopic details. In quantum chromodynamics, most of the mass of a proton comes from confined field energy rather than from quark rest masses. Gravity responds to the proton's total mass energy without regard for how it is partitioned internally. In nuclear reactions, binding energy changes the mass of nuclei, and gravitational effects reflect that change precisely. Precision measurements confirm this. When nuclei bind and release energy, the resulting mass difference can be measured and accounted for gravitationally. The equivalence between mass and energy is not a slogan. It is a quantitative statement verified to high accuracy. General relativity formalizes this through the energy-momentum tensor. This mathematical object encodes energy density, momentum flow, pressure, and stress. Space-time curvature responds to all of these components. Pressure contributes to gravity. Stress contributes to gravity. Radiation contributes to gravity. Even vacuum energy, whatever its true nature, enters the equations in the same way. This is why gravity is often described as the most democratic of interactions. It couples to everything that exists physically. It does not couple to charge, color, or flavor. It couples to presence. NASA descriptions of general relativity often emphasize this point by noting that gravity is sensitive to energy in all its forms. This sensitivity explains phenomena that would otherwise seem paradoxical. For example, a box filled with light weighs more than an empty box. The difference is tiny, but it is real and measurable in principle. Gravity accounts for the energy of the trapped radiation, just as it would account for matter. This universality also explains why attempts to modify gravity often face severe constraints. Any proposed theory must reproduce the observed equivalence between different energy forms. Deviations would show up immediately in precision tests of free fall, orbital dynamics, or gravitational lensing. So far, no such deviations have been observed. The story behind these tests is one of patience and refinement rather than sudden revelation. From early balance experiments to modern satellite missions, each generation pushed sensitivity further. ESA's microscope mission tested the equivalence principle to unprecedented precision, finding no violation. The result reinforces the idea that gravity does not care how mass is created. What gravity does care about is conservation. Energy, momentum must be conserved locally. How that energy moves and transforms shapes space-time curvature. But its origin, its internal structure, and its history are irrelevant to gravity's response. This indifference has profound implications. It allows physicists to treat vastly different systems within a single framework. A star, a cloud of radiation, a vacuum-dominated region, and a quantum field configuration can all be described gravitationally using the same equations. This unification is one of the great achievements of 20th century physics. It also sets boundaries on deeper theories. Any attempt to unify gravity with quantum mechanics must preserve this universality. A theory that assigns gravity preferential coupling to one form of energy would contradict a century of experimental evidence. Carl Sagan often spoke about the power of simple rules applied universally. Gravity's indifference to origin is one such rule. It is simple, but its consequences span the cosmos. There remain open questions. The precise nature of vacuum energy, the relationship between quantum fields and space-time geometry, and the role of gravity at the smallest scales are still under investigation. Observations from JWST and future missions may shed light on how energy behaved in the earliest moments of the universe, where gravity and quantum effects were both dominant. What is not in doubt is the principle itself. Gravity measures energy's presence, not its pedigree. It responds to what is there, not to how it came to be. If mass can arise from energy configurations, if inertia reflects how fields respond, if the vacuum itself participates, and if gravity responds to all of these without distinction, then mass no longer appears as a fundamental ingredient. It begins to resemble a recurring signature, one that emerges whenever energy becomes constrained in specific ways. Seen from that perspective, mass is no longer treated as a building block, but as an indicator of how energy organizes itself within spacetime. Part 10. Why might mass be an emergent signature, not a fundamental ingredient? Everywhere physics has looked closely enough, mass has appeared only after something else was already in place. It never shows up first. It follows structure. It follows constraint. It follows situations where energy, which otherwise moves freely, becomes organized in a way that resists change. That pattern is not philosophical. It is empirical, and it repeats across every scale where we have reliable data. At the smallest scales accessible to experiment, mass does not behave like a basic building block. In the standard model, the fundamental entities are fields. Particles appear as excitations of those fields, and their ability to possess rest mass depends on interaction. The Higgs field does not inject mass as a substance. It reshapes how certain fields relate energy to motion, allowing a rest frame to exist. Where that interaction is absent, as with photons, mass does not appear. This is not an interpretation layered on top of the data. It is exactly what collider experiments measure. Yet even that mechanism accounts for only a fraction of the mass we encounter. Protons and neutrons, which dominate the mass of ordinary matter, derive most of their mass from confined field energy. Quantum chromodynamics shows that gluon fields, under confinement, store enormous amounts of energy that cannot escape. That energy contributes directly to mass. Remove the confinement, and most of the mass disappears, even though the quarks remain. Again, mass follows structure, not constituents. At larger scales, the same pattern persists. Systems composed entirely of massless components can possess mass when energy is arranged in a configuration that admits a rest frame. Two photons moving in opposite directions form a system with invariant mass. Radiation trapped in a cavity adds weight to that cavity. These effects are not semantic. They are used daily in experimental particle physics, where invariant mass reconstruction is one of the most reliable tools available. Gravity reinforces this picture with striking consistency. In general relativity, space-time curvature responds to the full energy momentum content of a system. It does not respond to mass as an isolated concept. Binding energy gravitates. Radiation gravitates. Vacuum energy, whatever its ultimate origin, gravitates. Black holes formed from collapsing matter are indistinguishable from those that could, in principle, form from intense concentrations of radiation. Gravity measures presence, not pedigree. This universality places strong constraints on how mass can be interpreted. If mass were a fundamental ingredient, gravity would need to distinguish between energy that comes packaged as mass and energy that does not. No such distinction has ever been observed. Precision tests of the equivalence principle, including space-based experiments supported by ESA, show that objects fall identically regardless of internal composition. The gravitational field responds to total energy content with extraordinary fidelity. Inertia completes the pattern. Resistance to acceleration does not behave like a static property stored inside particles. It appears only when motion changes. It scales with total energy. Heating an object increases its inertial mass. Changing internal energy distributions changes resistance. These effects are small, but they are real and consistent with relativistic predictions. Inertia behaves like a reaction of field systems being forced out of equilibrium. The vacuum itself refuses to be excluded from this story. Quantum field theory shows that even in the absence of particles, fields retain fluctuations. These fluctuations produce measurable effects, from spontaneous emission to the Casimir force. Accelerated systems interact with this structured background. While physics does not yet claim that inertia is fully explained by vacuum interactions, it is clear that the vacuum is not passive. Any account of mass that ignores it remains incomplete. Across all these domains, the same theme emerges. Mass is not introduced as a primitive element. It appears when energy is constrained, balanced, confined, or symmetrically arranged. Where energy streams freely in a single direction, as with an isolated photon, mass does not appear. Where energy is trapped or internally balanced, mass does. This does not mean mass is illusory. It means mass is descriptive rather than foundational. It is a way of accounting for how energy behaves when freedom of motion is limited. In this sense, mass resembles other emergent quantities in physics. Temperature is not a fundamental ingredient of matter. It emerges from collective motion. Pressure is not a substance. It emerges from interactions. Mass, in modern physics, increasingly resembles these quantities rather than an indivisible atom of reality. NASA and ESA descriptions of fundamental physics often emphasize this layered structure. They present mass not as a standalone concept, but as something that arises from deeper mechanisms. JWST observations of early galaxies now show that massive structures formed rapidly once energy could settle into bound systems. The appearance of mass followed the appearance of structure. It did not precede it. It is important to be precise about what this view does and does not claim. Physics does not assert that mass is fully explained in all contexts. There are open questions. The precise origin of vacuum energy remains unresolved. The nature of dark matter, which gravitates but does not interact electromagnetically, is still unknown. Whether mass emerges from even deeper principles at the quantum gravity scale remains an active area of research. What is clear is that treating mass as a fundamental ingredient has become increasingly unnecessary. Every confirmed mechanism that produces mass does so through interaction and organization. No experiment has required the introduction of mass as an irreducible substance. This shift in perspective aligns with the broader trajectory of physics. Over time, concepts once considered fundamental often turn out to be effective descriptions. Absolute space gave way to space-time. Force gave way to interaction. Particles gave way to fields. Mass now appears to be following the same path. Carl Sagan often spoke about the power of asking where familiar ideas come from, rather than assuming they must exist. Mass, so central to everyday experience, turns out to be a remarkably subtle quantity when examined closely. It is not the starting point of physical explanation. It is a recurring signature that appears whenever energy loses the freedom to move without resistance. Seen this way, mass becomes a record rather than a cause. It records how energy is arranged within spacetime. It records how fields interact, how configurations stabilize, and how motion becomes constrained. Wherever those conditions are met, mass appears. Wherever they are not, it vanishes. This does not diminish the reality of mass. It deepens it. It places mass within a network of relationships that spans from quantum fields to cosmic structure. It allows the same concept to apply consistently to protons, photons, stars, and black holes without contradiction. As observations grow more precise and theories more unified, this view will continue to be tested. Future experiments may reveal deeper layers beneath the mechanisms we now understand. They may show that even fields and spacetime are emergent from something more fundamental still. If that happens, mass will likely follow the same pattern once again, appearing not as a primitive ingredient, but as a reliable signal of constraint and structure. For now, what physics offers is not a final answer, but a coherent one. Mass is not frozen energy. It is energy that cannot move freely. It is energy held in place by interaction, symmetry, and structure. It is a footprint left wherever motion meets resistance. As this long chain of ideas settles, there is no need to hold on tightly. The universe continues its work whether we watch or not. Fields interact, energy organizes, structure persists, and mass appears exactly where it must. Thank you for spending this time here and staying with the story all the way through. As the night settles and everything slows down, I hope the thoughts from this journey can rest easily in the background. Wishing you a peaceful, comfortable sleep and a gentle start when the next day arrives.